Welcome! In today's session, we will explore the problem number 897, titled Increasing Order Search Tree. This problem focuses on transforming a binary tree into a specific structure while maintaining the in-order traversal sequence. Let's dive in and break it down step by step. In this problem, we are given the root of a binary search tree, and the task is to rearrange the tree in order traversal so that the leftmost node becomes the root. Additionally, each node in the resulting tree should no longer have a left child and should only have one right child. Essentially, the output tree will be a right-skewed tree, where each node is connected to the next larger value through its right child. The input is represented as a tree node object, where each node contains a value, and pointers to its left and right children. The output is the root of the new tree that satisfies these conditions. Let's explore some examples to better understand the transformation. In the first example, the input binary search tree is visually represented to provide clarity. The tree starts with the root node of value 5, which branches into two subtrees, the left subtree rooted at 3 and the right subtree rooted at 6. The left subtree further branches down to 2 and 4, with 2 having its own left child of 1. On the right side, the subtree rooted at 6 connects to 8, which branches further into 7 and 9. The task is to rearrange this tree so that it becomes right-skewed. The resulting tree starts with 1 as the root, followed by 2 as its right child, then 3, 4, and so on, in ascending order of node values. Continuing from the transformation, the right-skewed tree expands further. After the node with value 5, the next node in the sequence is 6, which connects to 7, then 8, and finally 9. This ensures that every node only has a single right child, and all values are arranged sequentially in ascending order. The output of this transformation is represented as a list: 1, null, 2, null, 3, null, 4, null, 5, null, 6, null, 7, null, 8, null, 9. This linear representation highlights the structure of the right-skew tree. In the second example, the input tree is much simpler. It contains just 2 nodes, one is the root, with 2 as its right child. Since this tree is already in the desired right-skewed structure and follows in-order traversal, no changes are necessary. The output remains the same as the input. This demonstrates a scenario where the input tree already meets the problem's requirements, so it is returned as is. The output in this case is represented as 1, null, 2. The problem also comes with constraints and edge cases to consider. The tree can have between 1 and 100 nodes, and each node's value is unique and falls within the range of 0 to 10,000. Importantly, the input tree is always guaranteed to be a valid binary search tree. Some edge cases include a single node tree, where the output is identical to the input, and a tree that is already right-skewed, which also remains unchanged. On the other hand, for a left-skewed tree, the transformation will completely reverse its structure, converting it into a fully right-skewed tree. These constraints and edge cases help clarify the expectations for how the solution should handle different scenarios. To address the problem of rearranging a binary search tree into an increasing order search tree, one straightforward approach is to use a brute force method involving a list. The intuition here is simple. We know that performing an in-order traversal on a binary search tree yields the nodes in sorted order. So, we can use this property to solve the problem. First, we traverse the tree in in-order fashion, storing the nodes or their values in a list. Once we have this sorted list, we can iterate through it and construct a new tree where each node has only a right child. This keeps the nodes in the desired increasing order. While this approach is easy to understand and implement, it introduces additional space complexity since we store all the nodes in a list. The time complexity is linear, O(n), as we traverse the tree once and then construct the new tree from the list. However, the extra space requirement of O(n) for the list is a notable downside, making this approach less optimal in terms of memory usage. A more efficient solution builds on the same in-order traversal concept but avoids the extra space required for a list. Instead, we can modify the tree in place during the traversal. The key idea here is to maintain a reference to the last processed node and continuously attach the current node as the right child of that reference, while ensuring the left child is set to null. This approach starts with a dummy node to serve as the placeholder for the new tree, and as we traverse the original tree, we modify its structure directly. This method is more space efficient, requiring only O(h) space for the recursion stack, where h is the height of the tree. It's worth noting that H depends on the tree's structure, being O log n for balanced trees and O n for highly unbalanced ones. The advantage here is that we eliminate the need for a separate list, but this approach does require careful handling of pointers to avoid inadvertently breaking the original tree structure. For those seeking maximum space efficiency, the Morris traversal method offers an innovative solution. This technique performs an in-order traversal without using recursion or a stack. Instead, it temporarily modifies the tree into a threaded binary tree by creating links between nodes during traversal. As we traverse the tree in order, we can reconstruct the tree's structure so that each node only has a right child. After processing, the original tree structure can be restored if needed. The biggest advantage of Morris traversal is its O(1) space complexity, since it avoids both recursion and auxiliary data structures. However, the trade-off is complexity in implementation. The process of temporarily modifying the tree and managing these changes correctly demands careful attention to detail. Additionally, while each node is visited only twice, the temporary modifications introduce extra processing steps, making this approach more challenging to code and debug, particularly in high-pressure scenarios like coding interviews. Among the approaches considered, we've selected the optimized in-place reconstruction as the most practical solution for this problem. The key insight here is that the problem fundamentally requires in-order traversal to rearrange nodes in sorted order. By directly modifying the tree during traversal, we achieve an efficient solution without the added space overhead of storing nodes in a separate list. This approach is preferable to the brute force method because it avoids the O(n) space required for the list. While Morris traversal offers even better space efficiency with O(1) complexity, its added implementation complexity makes it less suitable, particularly in scenarios like interviews where simplicity and clarity are critical. The in-place reconstruction strikes the right balance between simplicity and efficiency, using O(h) space for the recursion stack, which is acceptable in most practical cases. For extremely unbalanced trees, where H approaches n, Morris traversal might be a better choice. However, for the majority of use cases, this in-place method is the most balanced and effective strategy. To tackle the problem of converting a binary search tree into an increasing order search tree, we start by using in-order traversal. This method is particularly suited for BSTs because it guarantees that we visit the nodes in sorted order. The process begins with the root node as input. From there, we recursively traverse the left subtree, process the current node by storing its value, and then move to the right subtree. As we perform this traversal, we collect the node values in a list. This list will be crucial because it preserves the sorted order of the BST elements, which is a key property we need for the next steps. Once we have the sorted list of node values, the next step is to construct the skewed tree. We start by initializing a dummy node, which acts as a placeholder for the beginning of the new tree. A pointer, called current, is used to keep track of the most recently added node in the skewed tree. With these preparations, we iterate through the sorted list. For each value in the list, we create a new node, attach it as the right child of the current node, and then update the pointer to this newly added node. By the end of this process, the right child of the dummy node becomes the root of the new skewed tree. Finally, we return this root as the result. The choice of in-order traversal is fundamental to this algorithm because it ensures the nodes are visited in sorted order. This eliminates the need for additional sorting and simplifies the process of building the skewed tree. The dummy node also plays an important role by providing a consistent starting point for the tree construction, avoiding edge cases when handling the root node. For data structures, we use a list to store the node values during the traversal, as it allows sequential access when constructing the tree. Additionally, the tree node structure represents each node in both the original BST and the resulting skewed tree. The key operations in this algorithm include the in-order traversal and the tree construction. The traversal visits each node exactly once, resulting in a time complexity of O(n), where n is the number of nodes in the BST. Similarly, constructing the tree by iterating through the list also takes O(n). To optimize, it's possible to combine these steps into a single pass. By constructing the skewed tree directly during the in-order traversal, we eliminate the need for the intermediate list, reducing the space complexity from O(n) to O(h), where h is the height of the BST. This approach is especially useful for large trees. Additionally, the algorithm handles edge cases gracefully, such as returning none for an empty tree or simply returning the root when the tree already has a single node. Analyzing the complexity of this algorithm, the time complexity is straightforward, O(n) for the traversal and O(n) for the construction, resulting in an overall complexity of O(n). For space complexity, the list of node values requires O(n) space, and the recursive stack for in-order traversal uses O(h), where h is the height of the tree. In the worst-case scenario, such as when the tree is already skewed, the height can be equal to the number of nodes, leading to a total space complexity of O(n). By implementing the single-pass optimization, the space complexity can be reduced to O(h) by eliminating the intermediate list, making the algorithm more efficient for tall, unbalanced trees. The problem requires transforming a binary search tree, BST, into an increasing-order search tree where every node only has a right child. This is achieved by performing an in-order traversal of the BST. In-order traversal naturally visits nodes in ascending order for a BST, making it ideal for this task. The treeNode class represents each node in the binary tree, with attributes for its value, val, left child, left, and right child, right. The increasing BST method in the solution class handles the transformation process. Inside the increasing BST method, we define a helper function in_order_traversal that recursively traverses the BST. This function takes a node as input and performs the following steps. 1. Base case, if the node is none, the function returns immediately. 2. Left subtree traversal, it recursively visits the left subtree to process nodes in ascending order. 3. Current node processing, the left child of the current node is set to none to eliminate the left reference, ensuring the tree becomes skewed. The current node is then attached to the right of the last processed node, tracked by self.current. The self.current pointer is updated to the current node. For right subtree traversal, it recursively visits the right subtree. A dummy node, with value -1, is created to act as the starting point for the new tree. The self.current pointer initially points to this dummy node. After the traversal is complete, the right child of the dummy node is returned, which points to the root of the new tree. This approach ensures that the tree is transformed in place, without creating unnecessary new nodes, and leverages the in-order traversal's natural ordering properties. The solution handles edge cases like an empty tree, where root is none, gracefully, returning none is expected. The implementation is clean, efficient, and adheres to the constraints of the problem. Here, we are defining the structure of our binary tree using the treeNode class. Each node has a value, a left child, and a right child. The constructor initializes these fields, with the left and right children set to null by default. Now, moving to the solution class, we introduce the increasing BST method, which is responsible for transforming the given binary search tree into an increasing order search tree. To begin, we create a dummy node with a value of -1. This dummy node acts as a placeholder to help us build the new tree incrementally. We also initialize a current pointer, which will keep track of the last node in the rearranged tree. Next, we perform an in-order traversal of the original tree. This traversal ensures that we visit nodes in sorted order, as required for the increasing order search tree. Finally, once the traversal is complete, we return dummy.right, which points to the root of the newly constructed tree. The in-order traversal method implements the in-order traversal logic. It first checks if the current node is null, in which case the method simply returns. Otherwise, it begins by traversing the left subtree, ensuring that all left descendants are processed first. After completing the left traversal, we handle the current node. We remove the left child reference by setting node.left to null, as the increasing order search tree should only have right children. Then, we attach the current node to the right of the current pointer, effectively adding it to the new tree. We move the current pointer to this node, so it's ready for the next insertion. Finally, we traverse the right subtree, processing the right descendants in sorted order. This approach ensures that all nodes are rearranged to meet the requirements of the increasing order search tree. To solve this problem, we start by looking at a simple binary search tree with 3 nodes, 2 as the root, 1 as the left child, and 3 as the right child. The first step is initialization, where we create a dummy node with a value of -1 and set a pointer, self.current, to point to this dummy node. This dummy node acts as a placeholder to simplify the process of building our result tree. Next, we perform an in-order traversal, which means we process nodes in the order of their left subtree, the node itself, and then the right subtree. Starting at the root node 2, we first traverse into its left subtree, which leads us to node 1. At node 1, since it has no left subtree, we process it by disconnecting its left child, setting node.left to none. Then, we attach node 1 to the right of self.current, which is currently pointing to the dummy node. This step begins to construct our increasing order tree. After attaching node 1, we move the self.current pointer to node 1, as it is now the last node in the restructured tree. Since node 1 has no right subtree, we return to process node 2. At node 2, we again disconnect its left child, setting node.left to none. We attach node 2 to the right of self.current, which now points to node 1. This ensures the increasing order is maintained. We then move self.current to node 2, making it the new end of our restructured tree, and proceed to traverse into the right subtree of node 2, which leads us to node 3. At node 3, both its left and right subtrees are none, so we directly process it by disconnecting its left child and attaching it to the right of self.current. Finally, we move self.current to node 3, completing the traversal for this tree. The resulting tree is a linked structure of nodes 1, 2, and 3, connected only through their right pointers. With the traversal complete, we return dummy.right, which points to the root of the newly constructed tree. The output is an increasing order tree where nodes are connected in ascending order as 1, 2, 3. Now, let's examine a more complex example with a larger binary search tree. This tree has 5 as the root, with 3 and 6 as its left and right children, respectively. Node 3 has 2 children, 2 and 4, while node 6 has a right child, 8. Additionally, node 2 has a left child, 1, and node 8 has a right child, 9. Following the same approach, we start by initializing a dummy node with value -1 and setting self.current to point to it. Then, we perform an in-order traversal to visit nodes in ascending order. Beginning at the root node 5, we traverse to its left subtree, reaching node 3, and continue traversing left until we reach the smallest node, which is node 1. Using the in-order traversal sequence, we process nodes in the order 1, 2, 3, 4, 5, 6, 8, and finally 9. At each step, for the current node being processed, we disconnect its left child by setting node.left to none, attach it to the right of self.current, and then move self.current to this node. This ensures all nodes are added to the restructured tree in ascending order. By the end of this traversal, the final tree is a right-skewed structure where the nodes are arranged as 1, 2, 3, 4, 5, 6, 8, 9. The root of this new tree is returned as dummy.right. For the final example, we consider a tree with just a single node, which is 1. The process remains consistent. We initialize a dummy node with value -1 and set self.current to point to it. Since the root node 1 has no left or right subtrees, we proceed to process it directly. We disconnect its left child by setting node.left to none, attach it to the right of self.current, and move self.current to node 1. The final tree is simply node 1, and we return dummy.right as the root of the restructured tree. There are a few key observations to highlight about this solution. First, the in-order traversal ensures that nodes are processed in ascending order, which is essential for constructing the increasing order tree. Second, using a dummy node simplifies the process of linking nodes, as we don't need to handle special cases for the first node in the sequence. Lastly, setting each node's left child to none ensures the tree adheres to the problem's requirements of having nodes connected only through their right pointers. This approach is both systematic and efficient, leveraging the inherent properties of in-order traversal and binary search trees. The time complexity of the increasing BST function is O(n), where n is the number of nodes in the binary search tree. This stems from the fact that the algorithm performs an in-order traversal of the tree, visiting each node exactly once. Let's break this down mathematically. During the traversal, the helper function in_order_traversal visits each node, and for each node, it performs two main operations, removing the left child reference and linking the current node to the right of the previous one. Both of these are constant time operations, O(1). Since there are n nodes in total and each node is processed exactly once, the total cost becomes O(1) multiplied by n, which simplifies to O(n). Importantly, this time complexity remains O(n) in all cases, whether the tree is balanced, skewed, or completely unbalanced, because the algorithm always traverses the entire tree regardless of its shape. The space complexity of the increasing VST function is O(h), where h is the height of the tree. This primarily accounts for the memory used by the recursion stack during the depth-first traversal. Let's analyze this further. The depth of the recursion stack directly depends on the height of the tree. In the case of a balanced binary tree, the height h is approximately log n, so the space complexity is O log n. However, in the worst-case scenario, where the tree is completely skewed either entirely to the left or the right, the height h becomes equal to n, and thus the space complexity increases to O(n). Additionally, the algorithm uses a small amount of constant memory for things like the dummy node and the self.current pointer, but this O(1) space is negligible compared to the recursion stack. Therefore, for the best case, which is a balanced tree, the space complexity is O log n. In the average case, if the tree is moderately balanced, the space complexity is also closer to O log n. For the worst case, where the tree is skewed, the space complexity becomes O(n). Now, let's compare the optimized approach to a naive method. A naive approach to solving this problem could involve performing an in-order traversal of the tree to collect all the node values into a list, sorting the list if necessary, and then reconstructing the tree in the desired order. This method, however, comes with higher costs. The time complexity would be O(n) for the traversal, O(n log n) for sorting, and O(n) for reconstructing the tree, resulting in a total time complexity of O(n log n). The space complexity for this naive approach would be O(n), due to additional memory needed to store the list of node values. In contrast, the optimized approach avoids the overhead of sorting and reconstruction by directly rearranging the nodes during the in-order traversal. This results in a time complexity of O(n), since each node is visited once, and a space complexity of O(h), where h is the height of the tree. To summarize the mathematical reasoning, the optimized method visits each node exactly once, performing constant work per node, leading to O(n) time. Space usage depends on the recursion stack, which is proportional to the tree height h. In a balanced tree, this is O log n, and in a skewed tree, it is O(n). When solving the increasing order search tree problem, there are several common mistakes to watch out for. One of the most frequent issues is skipping edge cases, such as not handling an empty tree, a tree with only one node, or highly unbalanced trees. These scenarios are crucial to consider because neglecting them can lead to runtime errors or incorrect outputs during testing. Another common mistake is implementing the in-order traversal incorrectly. For example, swapping the left and right subtree visits would break the sorted property of the binary search tree, resulting in an incorrect in-order sequence. Additionally, overusing space in a brute force approach is a pitfall to avoid. Some solutions involve storing the entire traversal in a list and then iterating over it again, which unnecessarily increases space complexity to O(n). Finally, misunderstanding recursive calls can lead to problems such as missing proper base cases. This can cause infinite recursion or stack overflows, which will crash the program or make it timeout. Identifying and addressing these errors is crucial to writing efficient and correct solutions. Another mistake to avoid is ignoring time-space trade-offs. While brute force solutions might handle smaller test cases, they often fail to scale for larger inputs due to inefficiency. It's important to evaluate whether a more optimized approach could reduce time or space complexity. In interviews, understanding certain patterns can give you an edge. Many binary search tree problems rely on in-order traversal to produce sorted outputs, so recognizing this can make solving such problems more intuitive. Optimization is another key aspect. Always analyze whether the solution can be achieved in O(h) or O log n time, where h is the height of the tree. This is especially relevant for well-balanced trees. It's also essential to clarify assumptions with your interviewer. For example, is the tree guaranteed to be a binary search tree? If not, you may need to validate the tree first, which can impact your approach. Lastly, be ready to discuss both iterative and recursive implementations. While recursive solutions are often simpler to write, iterative approaches are preferred in environments with stack depth limitations. To deepen your understanding, it's helpful to explore related problems that build on similar concepts. For instance, LeetCode 230 focuses on finding the kth smallest element in a binary search tree, while LeetCode 98 deals with validating whether a given tree is a binary search tree. LeetCode 173 introduces the concept of a binary search tree iterator, and LeetCode 530 challenges you to find the minimum absolute difference in BST values. In terms of alternative approaches, recursive in-order traversal is a classic method that's straightforward to implement, with a space complexity of O, H, where H is the height of the tree. However, it uses stack space, which can be a limitation in certain scenarios. Iterative in-order traversal avoids recursion and is more suitable for environments where stack overflow is a concern, though it can be slightly more complex to write. A more advanced technique is Morris traversal, which achieves O(1) space complexity. However, it temporarily modifies the tree structure, which may not be acceptable if the tree must remain unaltered. Understanding these trade-offs is key to selecting the best approach for a given problem. Lastly, for certain problems like finding the kth smallest element, you can combine binary search with tree properties to create highly efficient solutions. For example, by keeping track of the number of nodes in each subtree, you can narrow down your search range without fully traversing the tree. This approach leverages the inherent structure of binary search trees to minimize unnecessary computations, making it both time-efficient and space-efficient. Mastering this technique can be particularly useful for problems that require frequent queries or updates to the tree. By understanding and applying these strategies, you'll be well equipped to tackle a wide variety of binary search tree problems with confidence. Great job! Today, we tackled the increasing order search tree problem, focusing on restructuring a binary tree with in-order traversal. Remember to practice similar problems to strengthen your tree traversal skills. Thanks for tuning in, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!